Hello everyone, this is the second video lesson for the angles and circles unit of the Nat5 course. In this video we're going to take a little look at the third one in the list. Sorry, not the third one, the second one. And we look at finding right angled triangles inside the circle, and having found the right angled triangle, we can use some Pythagoras' theorem to help us solve some problems. So before we go into some examples, there are a couple of definitions here that I want to go through with you. Okay, the first one is called a perpendicular bisector. Right. Now, a perpendicular bisector is just a line that cuts another line in half at right angles. Now, if you think about it, the word perpendicular means to meet at right angles, bisect means to cut in half, so the perpendicular bisector would mean a line that cuts another line in half at right angles. So to show you an example of a perpendicular bisector on the diagram here, where what we've got is, where we'll be using these sorts of lines to help us solve the problems that you're going to see in the next couple of examples. So let's take a wee look here. I'm going to put on chord line. Okay, so we've got our chord, and from the center I'm going to draw out a radius. Now the radius will cut through the chord anywhere along this arc. Alright, but there is only one place along this arc where the radius line meets the chord line at right angles, and that would look to be about there. And what you've got is a right angle there, and because it's a perpendicular bisector to the chord, it cuts the chord line in half. Okay, so that's an example of a perpendicular bisector. Now you might be thinking, well, where's the right angle triangle in all of this, right? And how am I going to be able to use Pythagoras' theorem? Well, there is one more line I'm going to add to this diagram, and if I add this line on, you'll see the right angle triangle, and I'm hoping that you can see where it's going to be before I draw it. Here it's here. All right. So that line there is that makes the hypotenuse of the right angle triangle that you can see. Now, that line that I've just drew has a special name as well, because in relation to that circle, it isn't just the hypotenuse of that right angle triangle, but it's a radius. Yeah. So that can be quite a useful thing to remember as well. We've got our chord here, and this line here is another radius, right? Now, this is quite useful because what we're doing is using the right angle triangle here. We'll be able to, if we had enough information, we could do things like finding the height of this right angle triangle. Yeah, if I knew the other two sides, I could use Pythagoras to do that. I could also, if I knew the chord length and if I knew the height, I could find the radius of the triangle using Pythagoras' theorem. So these are the kinds of things that we're going to take a wee look at in the next couple of examples. So this is quite a typical one here. Find the length of x in the diagram. Now the key thing here is to solve problems, right? Using Pythagoras by now should be the easy bit of this, but you're going to be solving problems with this and using the fact that you can find right angled triangles in these pictures. So if you have a wee look at the diagram here, the first thing you should be doing is taking a look at what information you have, right? Well, we know the length of this chord line. That's 40 centimeters, okay? We know the distance between the center and the chord line is 15 centimeters, okay? So you should now be sort of saying to yourself, well, where can I get the right angle triangle out of all of this? Well, it comes really from here to here, right? Now, remember what I said in the previous page, that line there is a radius, yeah? And the side, the part of this diagram that we're trying to find, which is this bit here, this is also a radius, yeah? Radius line is just any line that goes from the center to the circumference. So if I used Pythagoras' theorem and found the hypotenuse of this triangle, right, then I would have found the radius, and by default I'll have found the value of x. So the first mark, when this comes up in the exam, the first mark is usually given for what's called marshalling your facts in a right angle triangle. So I would go away from the diagram, which can sometimes be quite busy and quite cluttered with lots of other information, and I would just draw out a simple right angle triangle and label it up. So we're trying to find the hypotenuse. We know that the height of the triangle is 15 centimeters, and the base of the right angle triangle isn't 40. Remember, this is a perpendicular bisector, so this line here of 15 centimeters cuts the chord in half, so that's 20 centimeters. So we've marshalled our facts, we've got our right angle triangle and all the information we've got. Let's use Pythagoras' theorem and solve. So we'll try to find a long side, so it'll be 20 squared and 15 squared. That comes to 625. And x will be the square root of 625. And so x is 25 centimeters. Right, so therefore the radius of that circle is 25 centimeters. Okay, let's have a look at another one. Calculate the length of x in this diagram. So, well, how is this diagram different to the last one then? Well, for starters, we know the radius of the circle. Right? In the last example, we didn't know the radius of the circle, but that's what we're finding. But in this example, we know it. So we know the radius is 6. The chord is what we're having to find here. We're having to find the length of that chord. So now that you've established some information here about this problem, look for the right angle triangle. Well, surely if you drop a line down onto there, that's going to make your right angle triangle. But the question is, we need to know, if we're going to do Pythagoras' theorem, we need to know 2 of the 3 sides. So I don't know this side, because that's part of the chord, but we need to use the information given here that this is 8 centimeters to help us find the height of the triangle. Well, if you move that 8 centimeter line over here, then that goes up there like that. But from the center to the circumference is a radius, so that has to be 6, which means the height of the triangle has to be 2. So that 6 and 2 makes the 8 centimeters. So now we've got all the information. Right? So get a separate diagram drawn, get the information written on it, 6 centimeters, 2 centimeters, and we need to find the base length of that triangle. Now, to save some confusion, it's x that's in the diagram there, but I'm not finding x right now, I'm only finding half of x, so I'm just going to call that y, just to, so that there's not any confusion over the x's, okay? So, y squared, we're finding a short side, so that's 6 squared, take away 2 squared. So y squared, well 6 squared is 36, take away 4 is 32, and so y will be the square root of 32, and the square root of 32 is 5.7 centimeters. Now that's only half the chord length, yeah? So x, this is why I was using different letters, x is going to be 2 times 5.7, yeah? So 2 times 5.7 is 11.4 centimeters. Okay. Let's have a look at, I've got one last example here to have a look at, right? This is a very, very typical exam question. And you might be able to tell from the image that I have actually pulled this one from a past paper, right? This is from an old credit maths past paper in the days before Nat5. Let's have a read through it. Water flows through a horizontal pipe of diameter 60 centimeters. Right, so that's a pretty key piece of information. The surface width, AB, right, where's AB? Right, AB's down here. That's a chord of that triangle, a chord of that circle. And the width of that is 55 centimeters. Okay, doke. We have to calculate the depth of water in the pipe. So we have to know what that is. Okay. Right. Well, just as in, there's a lot more sort of context and a bit of information to this, but just as in the last couple of examples, look for the right angled triangle. Right. Well, it's usually almost always in the same sort of place. Yeah. So there it's there. Okay. And you can see the diagram starting to get quite cluttered. I'm going to draw a triangle over on the right hand side in a wee second, but we need some information here. Well, this line here, right, from the centre to A, that's a radius line, and we know the diameter is 60 centimetres, so the radius is 30 centimetres. Okay. We also know from the chord being 55 centimetres that this side of the triangle, the base of this triangle, is going to be half of 55. Yeah? So half of 55 is 27.5. Right? So it's getting quite cluttered now. Let's draw my triangle out. Right? We've got 30 centimetres. We've got 27.5 centimetres. Right. What about that side? So we'll use Pythagoras' theorem now and work out that missing side. You might be wondering, well, why is he doing that? How's that going to help him establish a depth? Right. Well, I'll show you. Let's work out what this side is first, and I'll show you how you do that. So we're finding a short side here. So we do 30 squared, take away 27.5 squared. Right. 30 squared, grab the calculator, 30 squared, take away 27.5 squared, comes to 143.75, so we need to take the square root of that. And we get 11.98. Oh, that's good enough, we can just go for 12. Okay. So this height here is 12 centimeters. Now I'm just going to rub some of the annotations off. Now, just rubbing off the annotations there, right? And what we've got is that this part here is 12 centimeters. So that means the depth plus 12 must come to a radius, must come to 30. So the depth is going to be the radius length, 30, take away the height of that triangle. So that comes to 18 centimeters. The depth of water in the pipe. So you are now ready to try exercise 10.6. You're going to get that. That was the last exercise. You're going to get that finished. So you're going to go to question 4. from that exercise and just finish the rest of that exercise off. Okay, if you get stuck, send me pictures of the questions and I'll do you up a wee solution.